Morning to everyone. Today we are going to see about the Unit 3 Bandpass signal transmission and reception. Okay. So here we are going to see quadrature amplitude modulation. It is QAM. Okay. So what is quadrature amplitude modulation means? So before we are going to quadrature amplitude modulation, what is amplitude modulation we should know. Okay. So what is amplitude modulation means? Here the amplitude of the carrier wave is varied in accordance with the modulating signal. So that is amplitude modulation. Okay. So but in quadrature amplitude modulation, here both amplitude and phase components to provide a form of modulation. So both components are to provide a modulation, quadrature amplitude modulation. So that is able to provide the high level of spectrum usage efficiency. So the spectrum utilization is very, very efficient in quadrature amplitude modulation. Okay. Then the quadrature modulators and demodulators that are required to provide a capability to modulate both in phase and quadrature phase component. That means 90 degree in phase and out of phase. So quadrature components of the modulating signal on the carrier. So this modulation can be used for some analog transmissions, including AM and FM stereo transmissions, but it is for data applications. It has come to its own. Okay. So it is able to provide highly effective form of modulation for data, and it is used in everything from cellular phones to Wi-Fi and almost every other form of high-speed data communication system. So here you see about the in-phase component and quadrature phase signal. So this is this waveform indicate the in-phase signal component, and this one is the quadrature signal component. So this is the quadrature amplitude modulation concept. Okay. Then this QAM is a technique that this will, what is the quadrature amplitude modulation means? Here it mixes both amplitude and phase variations in the carrier at the same time. So in amplitude modulation, only the carrier wave is the amplitude of carrier wave. Only the amplitude is varied in accordance with the modulating signal. But in quadrature amplitude modulation, here both amplitude and phase variations in the carrier at the same time. Okay. So what is the techniques to do is follow higher data rates within the same bandwidth. Okay. So quadrature amplitude modulation is a signal. It has two carriers shifted in 90 degree. Okay. In phase by 90 degree. That is a sine wave or cosine wave are modulated and combined. So as a result, 90 degree phase difference, they are in quadrature, and this rise to the mean. Okay. So often it is one signal is called the in phase, that is I signal, and other is the quadrature or Q signal. Okay. So the resultant overall signal consisting of the combination of both I and Q carriers. It contains both amplitude and phase variations. Okay. So both amplitude and phase variations are present. It may be considered as a mixture of amplitude and phase modulation. So that is called quadrature amplitude modulation. Okay. The motivation behind the modulation is, it is the use of quadrature amplitude modulation comes from the fact that straight amplitude modulated signal and double sideband even with the suppressed carrier occupies twice the bandwidth of the modulating signal. Okay. So this is the motivation behind this modulation. Okay. The simple form of QAM is here we can tell is a 2 QAM. Okay, 2 QAM quadrature amplitude modulation. It is more commonly called QPSK or quadrature phase shift key. Okay. So it is produced by the circuit shown in figure. This circuit, this one, and it takes a serial bit stream and it passes through the 2-bit shift register. Okay. So show this figure. It takes the two serial bits. The bit streams are applied to the in a serial form. Okay. And it passes through a 2-bit shift register, and it producing two parallel bit stream at the half the rate. Okay. So one is called the in phase I bit stream and other quadrature Q bit stream. It is then both I and Q signals are each applied to a mixer along with the local oscillator. Okay. So the mixer output then part of the RF carrier Here note it, the LO signal, it is a local oscillator. That is local oscillator signal is applied directly to one mixer. So, but it is shifted by 90-degree phase shift and it is applied to the other mixer. Okay. So, the term quadrature means here shifted by 90 degrees. The two mixer outputs are AM signals, but at different phases. Okay. So, when they are added together, then QPSK signal is generated. So, with this arrangement, you can transmit at twice the rate of BPSK in the same bandwidth. Okay. Now, here see this diagram. Here is serial data. The data are serially given into the input of 2-bit register. Then one is applied to the mixer, then another one is, that means 90-degree in phase is applied to the mixer. Here another part is applied to the another mixer. So one is 90-degree in phase and one is 90-degree out of phase. Okay, that means the quadrature phase. Okay, so here I and Q signals, both signals are applied to the here adder. So this is the adder. Then the output signal is 2 QAM. That means quadrature amplitude modulated signal, or it is called QPSK signal. Okay. So this is the QPSK, quadrature amplitude modulation constellation diagram. So here the figure shows how we illustrate the constellation diagram in phasor and the quadrature phase diagram. Okay, so here the amplitude and phase of each possible combination of 2 bits. Okay, so the length of the arrow, it is called a phasor, the amplitude and the direction or angle in the phase. So the receiver gets a signal that is the phase of 135 degrees. It means 2-bit combination of 0, 1. It is being transmitted. So the cancellation diagram of B is usually shown without the arrows or it is phasor. So this is the constellation diagram. Okay. So here 16 QAM. So we already seen the 2 QAM, 2 QAM means it is a 2-bit 0, 0, 0, 1, 1, 0, 1, 1 combination. Okay. So here it is a 16-bit means it's a 4-bit combination. Okay. So here this is technique can be modified to produce 16 QAM, which transmits 4 bits per time interval or symbol causing the data rate to quadruple in same bandwidth. So here see that this is a 4-bit 0, 0, 0, 0, 0, 1. So likewise up to it is 1, 1, 0, 1 and 1, 1, 1. So the last one is 1, 1, 1, 1. So here 4-bit, that means 2 power 4, the 16-bit combination. Okay. So this circuit producing 16 QAM shown in figure. Here 4-bit shift register. In 2 QAM we use the 2-bit shift register. So here we are using 4-bit shift register. Okay, it produces 2 groups of I and Q bits. Okay, so there are converted into 4 levels by a 2 to 4 level converter, that is works like a digital to analog converter, DAC. Okay. So the resulting constellation diagram. So this is the constellation diagram of 16 QAM. Okay. So the common versions are 64 QAM and 256 QAM, which transmits 6 and 8 bits per symbol. Okay. So in the same bandwidth, and 1024 QAM is also an option in one system. Okay. So what are the applications of quadrature amplitude modulation? Okay. So here QPSK and QAM modulation methods are commonly used in cable TV. That means communication and digital TV as well as high-speed internet services. Okay. So they are used with the satellites and broadband wireless communications, all modern cell phone communication, cellular communications, and most of other digital wireless schemes use this type of modulation because of this efficient spectrum utilization. That means spectral efficiency. Okay. So here the transmitter and receiver diagram, the QAM enables 2 AM AC signals to be transmitted over the same frequency band and it conserving bandwidth. So the messages can be separated at the receiver. So this is accomplished by using 2 orthogonal carriers such as cosine and sine wave. So here M1 of t and M2 of t. So this is the transmitter and this is the receiver. Here it is a shift, phase shift. Okay, cos or sine phase shift, 90-degree phase shift. Pi by 2 means this is 180 divided by 2. It is 90-degree phase shift. Okay. Then this is the transmitted. S of t is a transmitted signal. Here receiver R of t is the received signal. Okay. So on the receiver side also the same signal is recovered by using the low pass filter. So this is LPF is low pass filter. This is the mixer. Okay. So the R of t is one part is applied to the one mixer, another part is applied to the another mixer. So then it will takes 90-degree in phase and quadrature phase. Then it is applied to the low pass filter. Finally, we got the original recovered input signal. Okay. So this is the equation of the quadrature amplitude modulation transmitter and receiver. So S of t means it's a quadrature amplitude modulated signal. Okay. Then M1 of t is first one signal and M2 of t is another signal. Okay. So you assume in phase and quadrature phase. Okay. So S of t it is equal to M1 of t cos omega ct plus M2 of t sin omega ct. So here M1 of t, M2 are the messages. You can think S of t as having a phase. So that is the sum of two phases perpendicular to each other. It is cosine leading the sine by pi by 2. Okay, so 90-degree in phase and 90-degree out, quadrature phase. So this it is a S of t equal to real time signal of M of t into e power j0 and plus M2 of t into e power minus j pi by 2 into e power j omega ct. Okay, so this is a phasor of M1 of t into e power j0. This is the phasor. M2 of t into minus j pi by 2, which is the sum of two perpendicular phasor. Okay, so these are the phasor signal in phase and quadrature phase. So we can interrupt QAM signal as a result of amplitude modulating the real and the imaginary part of complex signals. So M of t it is equal to M1 of t minus j M2 of t. So to simplify the computation of spectrum of S of t, so we can consider the messages M1 of t and M of t it is equal to M1 of t minus j M2 of t. So that is complex message. With the spectrum M omega it is equal to M1 of omega minus j M2 of omega. Okay. So that it is S of t equal to real term of M of t into e power j omega ct. So it is equal to 0.5 into M of t e power j omega ct plus it is a M star of M of t into e power minus j omega ct. So this is this star symbol indicates stands for complex conjugate. It is complex conjugate signal. The spectrum of S of t is then given by it is 0.5 into final M1 of omega minus omega ct minus j into M2 of omega minus omega c plus M1 of omega plus omega c plus j into M2 of omega c. Okay. So it is a superposition of spectra of two messages. So finally we got the bandwidth. It is 0.25 into M of t, M star of t. Okay. So likewise we get the second message. We can multiply S of t by S of omega ct and pass the resulting signal through the low pass filter. Okay. Then what is spread spectrum modulation? Okay, so here spread spectrum modulation is a very important one. That is SSM. So here a collective class of signaling techniques are employed before transmitting the signal to provide a secure communication. That is known as spread spectrum modulation. So the advantage, as a main advantage of this spread spectrum communication, it is to prevent interference, whether it is intentional or unintentional. Okay, so to prevent the interference is the main advantage of spread spectrum modulation. Okay, so here the signal modulated with these techniques are hard to interface and cannot be jammed. We are not able to jam the signal. So an intruder with no official access is never allowed to crack them. So hence these techniques are, it is very, very security because, okay. So it is used for military purpose. So these spectrum signal transmit at low power intensity and as a wide spread of signals. Okay, wide spread of signals. Here, see that here there are two bandwidth involved here. So one is modulated signal, that is the modulated signal, and the spreading sequence. Okay. So the first will be very much less than the second. And the output spread spectrum signal will be spread either side the original RF carrier by the amount of to the bandwidth of PN sequence. So here this is the mixer modulated signals and PN sequence. Okay. So the modulated signals applied to the mixer and PN, that is the pseudo random sequence. Okay. So it is applied to the mixer. So both are spreaded. Then the output is a spread spectrum signal. Then what is a direct sequence spread spectrum? Okay. The direct spread spectrum sequence. So direct sequence spread spectrum also, it is a code division multiple access, DSCDMA. It is two approaches to spread spectrum modulation for digital transmission over the airways. So one of the approaches here, DSCDMA, direct sequence spread spectrum. Here stream of information to be transmitted. That means the serial of stream of information to transmitted and divided into small pieces. Okay, so each of which is allocated across a frequency channel across the spectrum. So here the data signal at the point of transmission is combined with a higher data rate bit sequence. So also it is known as chipping codes. So that divides the data according to a spread ratio. So here the redundant chipping code helps the signal resist interference, and also it enables the original data to be recovered and the data are damaged during the transmission. So the direct sequence with the direct spread spectrum process known as frequency hopping spread spectrum or frequency hopping code division multiple access. So it's a broad slice of the bandwidth spectrum is divided into many possible broadcast frequencies. Normally, in general, the frequency hopping devices use the less power and or it is very cheaper. But the performance of DSCDMA system is usually better and more reliable. Okay. So compared to frequency hopping devices, the DSCDMA is very reliable and more better. So the spread spectrum first was developed for use by military because it is uses wideband signals and are difficult to detect or difficult to crack the signal, and that resists the attempts at jamming. So in recent years, researchers have tuned their attention applying spread spectrum processes for commercial purposes. So especially in local area wireless network. So this is the block diagram of direct sequence spread spectrum network. So here see this RF carrier is one of the input and bipolar message, that is zeros and ones. The digital binary bits are the another input. So here the modulated signal can be any type, but typically digitally derived such as binary phase shift keying, BPSK. So binary phase shift keying. Okay. So the output is the RF carrier and the bipolar message mixed together. The output is binary phase shift keying. So this BPSK signal is applied to the mixer. Then pseudo random noise is applied to another one side. Both are mixed together here. The output is a direct sequence spread spectrum modulated signal. Okay. So this arrangement of the signal is simplified, and it is a clock for the bipolar. It is a sub-multiple of clock of PN sequence. Then the modulo 2 sum of the message and PN sequence can be used to multiply the RF carrier and generating DSSS signal with a single, it is multiplier. Okay. The next one is frequency hopped spread spectrum. Okay. So this is the frequency hope technique. Here, the users are made to change the frequencies of usage from one to another in a specified time interval. So here the users can able to space or change the frequency usage and for the specified time interval, a fixed time interval. So hence it is called a frequency hopping. So for example, the frequency was alerted to one sender or one user, okay, for a particular period of time. Now, after the center one goes to the other frequency. So initially, he or she in the one frequency. Then after that, it will change to the another frequency, and sender 2 uses the first frequency. Okay. So which was previously used by the center one or user one. So this is called frequency use. Okay. So the frequencies of the data are hopped from one user to another user to provide a secure transmission. So the amount of time spent on each frequency hop is called as a dwell time. Okay. So this is the frequency hop spread spectrum transmitter. Okay. So here the input is binary data. It is applied to the modulator, that is frequency shift keying or binary shift keying. Then it is applied to the frequency hop spreader. So in the frequency hop spreader, here it is a mixer, frequency synthesizer and channel table, then pseudo random bit source. Okay. Then after that, the band pass filter, then the output is spread spectrum signal, that is S of t. Okay. So here the block diagram, here the baseband signal is then modulated on a carrier C of t. Then the frequency of carrier, the C of t, the sequence of channels. So it is depends on the spreading code which is generated by the pseudo random source. So every t seconds, tc seconds, the PN source produces a new k bit value. Okay. So this value then used to look up a channel in the channel table, and that determines the frequency of carrier signal for C of t means carrier signal for that time interval. Okay. So this is the comparison of frequency hop spread spectrum and direct sequence spread spectrum. That means CDMA. The direct sequence spread spectrum, CDMA means co-division multiple access. So here the first difference is multiple frequencies are used in frequency hopped spread spectrum, because here the frequency is hopped from one user to another user. Okay, it's shifting from one user to another user. Okay, so here only single frequency is used in DSSS. Okay, then in frequency hop spread spectrum, hard to find the user frequency at any instant of time. Here the user frequency once allotted is always the same frequency. The frequency reuse is allowed in FHSS and frequency reuse is not allowed in DSSS. And sender need not to wait in FHS. Then sender has to wait in spectrum. Suppose the spectrum is busy, then sender need to wait. The next one is power strength of the signal is very high in frequency hop spread spectrum, but in DSS, power strength of the signal is low. Then in FHS, the stronger and penetrates through the obstacle, but in direct sequence spread spectrum, it is weaker compared to the frequency hop spread spectrum. Then in FHS, it is never affected by the interference and it is very cheaper and it is commonly used technique. But in DSSS, it can be affected by interference also. It is expensive and it is not frequently used. So this is the comparison between the frequency hop spread spectrum and direct sequence spread spectrum. Okay. Then what are the advantages of using the spread spectrum techniques? Okay, so these are the following advantages of spread spectrum. So here crosstalk elimination and better output with the data integrity, and it reduce the effect of multipath affecting and better security because it cannot able to crack easily. Okay, then it reduce the noise, then coexistence with other systems and longer operative distance. It is used for long distance communication and it is hard to detect and we can not easy to demodulate and decode. So these are the security purpose. Okay, difficult to jam the signal. Okay, so although the spread spectrum techniques were originally designed for military uses, okay, they are now being used widely for commercial purpose. Thank you.